The welcomes have to wait for the photographs to finish. Welcome, everybody, to this event. I'm so pleased that you all can be here. It is a beautiful morning, it's a beautiful venue, and we've got a lot to discuss and to celebrate this morning. My name is Dr. Helen Chersky. I'm an academic physicist and a writer and broadcaster based in London, in the United Kingdom, and it's my job this morning to guide you through the ceremony. And I would like to welcome not only all of you who are here in Hamburg with us, but also the guests on the live stream. We have people watching us from around the world, and also a special welcome to the first mayor of Hamburg, Dr. Peter Tschentscher, and he will be addressing us later on. This event will mainly be in English, with some parts in German, and there are headphones. Hopefully you will have seen them at the back, so simultaneous translation is available. And to get us started in this event, which is very appropriate in this beautiful venue, we are going to have some beautiful music. And I would like to introduce Fabian Egger on the flute, Johann Zau on the piano. Both are prize winners and scholars of the Foundation Deutsche Stiftung Musikleben. And they will play for us the Sonata in F major by Georg Philipp Telemann. Well, after that wonderful start, it's my great pleasure to welcome the first Mayor of Hamburg, Dr. Peter Tschentscher, to the stage to give a welcome address.
Sehr geehrter Herr Professor Hyman, sehr geehrter Herr Dittmar, Herr Professor Stratmann, Herr Vizepräsident der Hamburgischen Bürgerschaft, sehr geehrte Frau Generalkonsulin, sehr geehrte Damen und Herren, herzlich willkommen im Hamburger Rathaus zur Verleihung des Körber Preises für die europäische Wissenschaft 2022. Seit fast 40 Jahren würdigt die Körber-Stiftung herausragende Leistungen von Wissenschaftlerinnen und Wissenschaftlern im Bereich Physical and Life Sciences. Das Besondere an den ausgezeichneten Arbeiten ist ihr Anwendungsbezug. Wer den Körber-Preis erhält, hat für die großen Herausforderungen unserer Zeit Fortschritte ermöglicht und neue Perspektiven eröffnet. Der Körber-Preis hat international einen hervorragenden Ruf und zählt zu den höchst dotiertesten Wissenschaftspreisen der Welt. Frühere Preisträgerinnen und Preisträger haben das Verhalten des AIDS-auslösenden HIV-Virus erforscht, Erkenntnisse über die Entstehung von Krebs gewonnen oder neue Behandlungsmethoden für Erblindete entwickelt. 7 Körber-Preisträgerinnen und Preisträger haben später auch den Nobelpreis erhalten. Als der Körber-Preis 1985 zum ersten Mal vergeben wurde, hatten Kurt A. Körber und der damalige Vorsitzende des Preiskuratoriums, Professor Reimer Lüst, neben der Förderung wissenschaftlicher Exzellenz in Europa ein weiteres Ziel. Sie wollten mitten im Kalten Krieg die Menschen und vor allem Wissenschaftlerinnen und Wissenschaftler über Systemgrenzen hinweg miteinander verbinden. In den Anfangsjahren wurde der Körber Prize daher ausschließlich für gemeinsame Arbeiten von Forscherinnen und Forschern aus Ost- und Westeuropa vergeben. Mit der Mission, in politisch schwierigen Zeiten Brücken zu bauen, passte die Körber-Stiftung von Beginn an zu der weltoffenen Handels- und Hafenstadt Hamburg, die sich seit jeher für internationale Verständigung und Zusammenarbeit einsetzt. Um zur Annäherung zwischen der damaligen Bundesrepublik Deutschland und der DDR beizutragen, schloss Hamburg 1987 eine Städtepartnerschaft mit Dresden, der Wirkungsstätte des heutigen Preisträgers. Seit dem Fall der Mauer und dem Zusammenwachsen Europas ist Ost-West-Kooperation keine Bedingung mehr für die Preisvergabe. Dennoch steht der Körber-Preis 2022 unter dem Eindruck der Ereignisse der vergangenen Monate. Der Krieg gegen die Ukraine hat uns vor Augen geführt, dass Frieden und Sicherheit in Europa auch im 21. Jahrhundert leider keine Selbstverständlichkeit sind. Zugleich zeigt das gemeinsame und entschiedene Vorgehen der Mitgliedstaaten der Europäischen Union, ihre gemeinsame Reaktion auf die russische Aggression, dass der Prozess der europäischen Integration vorangekommen und eine gemeinsame politische Haltung über nationalstaatliche Grenzen hinweg entstanden ist. Gerade in der Forschung ist die grenzüberschreitende Kooperation heute selbstverständlich und die Lebensläufe von Forscherinnen und Forschern sind international. Das zeigt auch die Biografie des diesjährigen Körber-Preisträgers. Anthony Hyman wurde in Israel geboren. Er hat in Großbritannien Zoologie studiert, in Zellbiologie promoviert und seine wissenschaftliche Laufbahn in den USA begonnen. Inzwischen lebt und forscht er seit über 30 Jahren in Deutschland, zuerst in Heidelberg und seit 1999 in unserer Partnerstadt Dresden. Dort hat Anthony Hyman das Max-Planck-Institut für molekulare Zellbiologie und Genetik mit aufgebaut. Er forscht mit seinem Team an der Schnittstelle zwischen Medizin und Biologie und untersucht die Funktionsweise von Zellen, also den kleinsten lebenden Einheiten aller Organismen. 2009 hat er einen bis dahin unbekannten Materialzustand von Proteinen in der Zellflüssigkeit entdeckt, die sich in kleinen Tropfen, sogenannten Kondensaten, konzentrieren und dadurch spezielle biochemische Reaktionen in den Zellen ermöglichen. Normalerweise werden diese Zelltröpfchen schnell wieder abgebaut. Ist dieser Abbau jedoch gestört, können toxische Ablagerungen entstehen, die mit schwersten neurodegenerativen Erkrankungen wie amyotropher Lateralsklerose oder Alzheimer in Verbindung gebracht werden. Anthony Hyman und sein Team untersuchen, wie Zellen die Bildung und den Abbau von Proteinkondensaten steuern und wie sich Störungen dieser Abläufe beheben lassen. Daraus können sich wichtige Erkenntnisse ergeben zu den Ursachen und für die Behandlung, vielleicht sogar die Heilung von Erkrankungen, denen die Medizin bislang weitgehend ohne wirksame Therapieoptionen gegenübersteht. Meine sehr geehrten Damen und Herren, mit Anthony Hyman erhält heute erneut ein Forscher den Körber-Preis, der auf seinem Fachgebiet Pionierarbeit leistet. Die Entdeckung der Zellkondensate hat ein neues Kapitel eröffnet, das inzwischen zu den vielversprechendsten Forschungsfeldern in der Molekularbiologie gehört. Durch den Aufbau des Max-Planck-Instituts für molekulare Zellbiologie und Genetik in Dresden hat Anthony Hyman sich zudem in hohem Maße um den Wissenschafts- und Forschungsstandort Deutschland verdient gemacht. Lieber Herr Hyman, im Namen des Senats der Freien und Hansestadt Hamburg gratuliere ich Ihnen sehr herzlich zum Körber-Preis für die europäische Wissenschaft 2022. Ich wünsche Ihnen und Ihrem Team in Dresden weiterhin viel Erfolg für Ihre wissenschaftliche Arbeit und auch persönlich alles Gute. Herzlichen Dank.
Thank you very much, Dr. Peter Tschentscher. I would now like to introduce Dr. Lothar Dittmar, who is the chairman of the executive board of Körber-Stiftung.
Sehr geehrter Herr Erster Bürgermeister, lieber Herr Tschentscher, sehr geehrte Frau Wissenschaftssenatorin, liebe Frau Fegebank, lieber Professor Hyman, liebe Gremienmitglieder des Körber-Preises, meine sehr verehrten Damen und Herren, auch von meiner Seite noch einmal ein herzliches Willkommen. Kurt Körber hatte in den 1980er Jahren eine Vision. Er wollte mit dem Körber-Preis Wissenschaftlerinnen und Wissenschaftler auszeichnen, deren Forschung, und jetzt zitiere ich ihn, einen wesentlichen Beitrag zur Erhaltung der Lebensbedingungen auf unserem Planeten zu liefern versprechen. Das ist eine extrem anspruchsvolle Erwartung und sie ist auch nicht unbedingt kompatibel mit dem Selbstverständnis von Forscherinnen und Forschern. Denn die Wissenschaft weigert sich, durchaus zu Recht, nur unter dem Aspekt der Nützlichkeit und der gesellschaftlichen Relevanz beurteilt zu werden. Diese Freiheit dient am Ende ja auch uns allen, denn spektakuläre wissenschaftliche Durchbrüche geschehen meistens dort, wo man sie nicht erwartet. Es lohnt sich daran zu erinnern, dass kein Politiker jemals die Erfindung eines Computers oder Mobiltelefons gefordert hat. Der Computer wurde sogar maßgeblich an einem Institut in Princeton entwickelt, das eigens für die zweckfreie Grundlagenforschung eingerichtet worden war. Und natürlich spielt auch der Zufall eine Rolle. 1928 ließ Alexander Fleming während des Sommerurlaubs das Fenster seines Labors in London offen. So landeten Pilzsporen auf den Eitererregern, mit denen er experimentierte. Aus der scheinbaren Gammelmischung wurde einer der wichtigsten Arzneistoffe des Jahrhunderts, Penicillin. Viele Geschichten in der Wissenschaft gehen so und sie stehen in einem scheinbaren Widerspruch zum Wunsch unseres Stifters. Wie geht das zusammen? Zunächst einmal, anders als vor 40 Jahren, so alt ist nämlich Körbers Forderung, reden wir heute ja tatsächlich über die Erhaltung der Lebensbedingungen auf diesem Planeten. Deshalb muss die Frage erlaubt sein, wird die Wissenschaft dem eigentlich gerecht? Dient sie uns ausreichend als Frühwarnsystem und gibt sie uns Instrumente an die Hand, um auf Problemlagen zu reagieren? Dazu ein kurzer Faktencheck und ich möchte ihn gerne an den beiden größten Krisen unserer Zeit machen, der Corona-Pandemie und dem Klimawandel. Ernstzunehmende Hinweise auf einen Klimawandel haben sich über einen Zeitraum von inzwischen 80 Jahren verdichtet. In den 60er und 70er Jahren des letzten Jahrhunderts ist auch die klimaerwärmende Wirkung der stetig ansteigenden Konzentration von Kohlenstoffdioxid in der Erdatmosphäre verifiziert. Und seit den späten 1980er Jahren gibt es Computermodelle für ein tieferes Verständnis dieser Entwicklung. Ein Pionier dieser Modellierung war Klaus Hasselmann, der genau an dieser Stelle 1990 dafür mit dem Körber-Preis ausgezeichnet worden ist und im letzten Jahr den Nobelpreis erhalten hat. Pandemien und Seuchen sind anders als der Klimawandel stetiger Begleiter der Menschheit in ihrer Geschichte gewesen und es hat viele Maßnahmen zur Bekämpfung gegeben. Neu ist allerdings, dass ähnlich wie in der Klimaforschung inzwischen auch Modellierungen möglich sind. Und so hat etwa das Robert-Koch-Institut 2013 ein Pandemieszenario entwickelt, das auf den Erfahrungen der Vergangenheit beruhte. Für den hypothetischen Modisas-Erreger wurde angenommen, dass er irgendwo auf einem Markt in Südostasien von einem Wildtier auf einen Menschen übertragen werden würde und sich dann über die Welt ausbreiten würde. Eine im Rückblick schaurig präzise Vorwegnahme des Geschehens 2020. Halten wir also fest, das Frühwarnsystemwissenschaft funktioniert. Zum zweiten Aspekt, den Maßnahmen, den Möglichkeiten zur Bewältigung von Krisen. Und erneut beginne ich mit dem Klimawandel. Wissenschaftliche und technologische Lösungen zur Reduktion von CO2 und zur alternativen Gewinnung von Energie gibt es seit Jahrzehnten. Die lange Zeit größte Versuchsanlage der Welt für Windkraft, der Grovian, ging 1983 in der Nähe von Mahne in Betrieb. 1991 wurde das erste deutsche Passivhaus gebaut. 1999 brachte ein großer Kfz-Hersteller das erste 3-Liter-Auto an den Markt. Seit 1988 bündelt der Weltklimarat den aktuellen Wissensstand und stellt der Politik Daten zur Verfügung. Vergleichbares geschieht auch in Deutschland, etwa durch die Nationale Akademie Leopoldina. Die Wissenschaft macht ihren Job. Sehr beeindruckend war und ist auch die Antwort der Wissenschaft auf Corona. Kaum war das Virus in der Welt, wurde ein riesiger Apparat in Bewegung gesetzt, um die Verbreitung der Ansteckungswege zu verfolgen, um Reproduktionsraten zu erheben, Krankheitsbilder zu beschreiben und Empfehlungen abzugeben. Der eigentliche Triumph der Wissenschaft war aber ein anderer Durchbruch. In absolut rekordverdächtiger Zeit stand der erste Impfstoff bereit. Sie werden das erinnern, am 26. Dezember 2020, nicht einmal ein Jahr nach dem Ausbruch von Corona in Deutschland, fand hierzulande die erste Impfung statt. Das Wunder der Impfstoffentwicklung in Rekordzeit ist allerdings jetzt einen zweiten Blick wert. Denn hier wird einmal mehr deutlich, wie wichtig eine möglichst breit angelegte Forschung ist. An der neuen Impfstofftechnik auf mRNA-Basis wurde schon seit Jahrzehnten gearbeitet, allerdings mit einem ganz anderen Ziel, nämlich um einen Impfstoff gegen Krebs zu entwickeln. Nur so gab es eine Grundlage, auf der sich die Forscherinnen und Forscher atemberaubend schnell mit der neuen Gefahr auseinandersetzen konnten. Was hier deutlich wird, ist, Forschungsfreiheit und Grundlagenforschung stehen nicht im Gegensatz zum Nutzen für die Menschen, sondern sie sind in vielen Fällen, so paradox das klingt, der kürzere Weg zum Erfolg. Eine Forschung, die möglichst breit angelegt ist, die sich auf unbekanntes Gebiet vorwagt, die ganz großen Fragen beantworten will, kann scheitern. Das ist bei jeder Entdeckungsreise der Fall und sie endet vielleicht auch nicht in Indien, sondern in Amerika. Aber der Ertrag ist beim Erfolg ungleich größer. Es wird eben nicht nur das vorhandene Land genauer kartiert, sondern gleich ein neuer Kontinent entdeckt. So funktionieren wissenschaftliche Revolutionen und das ist der Wert einer Forschung, die auf Erweiterung der Grundlagen und nicht auf den schnellen Nutzen zielt. Grundlagenforschung ist allerdings leider in vielerlei Hinsicht eine Art Fremdkörper in der heutigen Welt. Wir wollen unbedingt schon am Anfang wissen, was wir für unser Geld bekommen, oder zumindest möchten wir garantiert haben, dass der eingeschlagene Weg am Ende dann auch wirklich dazu führt, dass eine schwere Krankheit besiegt oder die Supraleitung gefunden wird. Und natürlich soll der Einsatz an Mitteln auch nicht zu groß sein. Schlanke und effiziente Strukturen sind das Signum unserer Zeit. Auch hierzu verhält sich Grundlagenforschung wie ein störrisches Relikt. Sie braucht nämlich eine ausreichende Infrastruktur, um erfolgreich zu sein. Das DESI ist nicht für den halben Preis zu haben. Und schließlich darf es gerne schnell gehen, denn wir sind an den Rhythmus von Quartalsergebnissen, Jahresplänen und Wahlperioden gewöhnt. Auch dem entzieht sich eine Forschung umso mehr, je stärker sie das Ganze in den Blick nimmt. Wenn es um die Verbesserung der Lebensbedingungen auf unserem Planeten geht, dann kann das schon mal einen Moment in Anspruch nehmen. Am Ende hat es auch Körber akzeptiert und der Forschung ein anderes Zeitmaß als seinem Unternehmen zugeteilt. Zum Glück ist Körber aber nicht von seinem Anspruch abgerückt, den Forscher auch als Unternehmer zu sehen. Denn das hat am Ende dazu geführt, das Preisgeld ohne Antragswesen, ohne Verwendungsnachweise, ohne Sachstandsberichte zu gewähren. Es ist, wenn Sie so wollen, Risikokapital für die Preisträgerin oder den Preisträger. Für uns ist das Wagnis, ehrlich gesagt, überschaubar. Hochgradig intrinsisch motivierte Menschen arbeiten bekanntermaßen besser und erfolgreicher als solche, die engmaschig kontrolliert werden. Und im Übrigen gibt uns die faktische Bilanz recht. Jenseits ihrer Forschung haben fast alle unsere letzten Preisträgerinnen und Preisträger Firmen gegründet, um auch das Anwendungspotenzial zu heben. Die wissenschaftliche Exzellenz unserer Preisträgerinnen und Preisträger steht außer Frage. Es wurde eben schon gesagt, 7 der Körber-Preisträger haben auch den Nobelpreis erhalten. Meine Damen und Herren, alles, was ich bisher gesagt habe, manifestiert sich, Sie ahnen es, hier im Saal in der Person unseres heutigen Preisträgers Anthony Hyman. Er ist Grundlagenforscher und hat gewissermaßen einen neuen Kontinent betreten und eine völlig neue Form biologischer Materie entdeckt, die schon erwähnten Kondensate im Inneren von Zellen, Proteine, die sich ohne trennende Membran zu Verbündeten zusammenschließen. Sie merken schon, das ist schwer in einem Satz zu erklären, aber gleich hören Sie mehr dazu vom Preisträger selbst. Dieser bislang nie gesehene Mechanismus erlaubt neue und sehr fundamentale Einsichten in das Funktionieren von Zellen und er hat vermutlich, muss man an dieser Stelle sagen, ein sehr großes Anwendungspotenzial. Die Entstehung von neurodegenerativen Erkrankungen ist schon erwähnt worden und die Möglichkeit, darauf auch zu reagieren. Anthony Hyman ist noch einen Schritt weiter gegangen und hat sich auf die Suche nach Reagenzien gemacht, die dieser Verfestigung vorbeugen oder sie sogar wieder auflösen können. Und natürlich trägt er das Körber-Gen in sich und ist Co-Gründer einer Firma, die sich der Medikamentenentwicklung auf Basis seiner Entdeckungen verschrieben hat. Lieber Herr Professor Hyman, unser Stifter Kurt Körber wäre als rastloser Erfinder von Ihren Entdeckungen ebenso begeistert gewesen wie als umtriebiger Geschäftsmann von Ihrer Unternehmensgründung. Herzlichen Dank für Ihre großartige Arbeit und die ebenso herzlichen Glückwünsche im Namen der Körber-Stiftung und auch unserer Gremien zum Körber-Preis für die europäische Wissenschaft 2022. Mein Dank für die Wahl des Preisträgers geht wie immer an unsere Gremien, das Search Committee und das Kuratorium, die sich erneut für eine hochkarätige und innovative Entscheidung gesorgt haben. Sehr froh sind wir, uns wieder ohne Beschränkungen hier im Festsaal des Rathauses versammeln zu können. Ein Gruß soll sein an die vielen, die die Veranstaltung heute per Stream verfolgen. Ich danke Ihnen, lieber Herr Tschentscher, und Ihnen, liebe Frau Fegebank, dafür, dass Sie uns erneut die Gastfreundschaft in diesem wunderschönen Saal gewähren. Wir empfinden das als große Wertschätzung. Und damit übergebe ich an unsere Moderatorin Helen Czerski, die uns jetzt zusammen mit Anthony Hyman einen Blick in das Innenleben der Zelle eröffnen wird. Herzlichen Dank.
Thank you very much to Dr. Lothar Dittmar. Now, I'm sure you're ready to meet our prize winner. And to introduce him, we have a film that was made by Wagner Vision about Anthony Hyman's research, his team, and his research in Dresden in Germany. So here is the introduction.
Clouds are fascinating to watch. Amazingly, every day, a process comparable to cloud formation occurs in the billions of cells that make up our bodies. The biologist Tony Hyman and his team investigate this process.
The miracle of life is something that we enjoy every single day. It's like peeling back the layers of an orange and seeing more and more interesting details as we go further inside.
But what does his research have to do with clouds? Or with possible cures for illnesses such as Alzheimer's disease? To find out, we accompany Tony Hyman to his lab at the Max Planck Institute for Molecular Cell Biology and Genetics in Dresden, Germany, which he's headed for over 20 years. His special area of expertise is the inside of cells, specifically the proteins that occur within the intracellular fluid. These so-called condensates visible here as an aggregation of white dots, form under very specific conditions, much like clouds.
One way to think about it is when you see clouds forming in the sky. As things like temperature or pressure change, the water molecules suddenly condense to make clouds. And this process of condensation is similar to the type of process we look at inside the cell.
That condensation of proteins takes place inside our cells is a groundbreaking discovery, critical for understanding many biological processes.
Hey, Natasha.
Here, these processes are put under the microscope.
What are we looking at today?
We're looking at GFP.
A model organism is of great help in this endeavour. The nematode C. elegans unwittingly discloses his innermost secrets to the researchers. The threadworm's gonads, responsible for reproduction, are of particular interest to Tony Hyman and his team.
They just want to move. Okay, good. All right, can't ask for better than that. The formation of what we call germ cells, what you know as sperm and oocytes, is a fascinating process because while our somatic cells, our body cells, age, the germ cells do not. They're immortal. So each generation, the cell has to maintain the immortality of its germ cells.
Change the color, and then I'll check the other channel. Okay, very nice.
A fluorescence microscope reveals the secret hidden inside the threadworm's gonads.
Okay. Can you show me the strains from last week?
Here, the importance of protein condensates for the nematode's reproduction comes to light. The greenish clusters are condensates known as P granules, and these are necessary to form egg cells.
The oocyte, and this is the gonad. P granules, if they don't form, result in a worm that grows up but has no germ cells. It'd be like you're born, you grow up, but you're sterile. So they play a crucial role in our understanding of how cells go ahead and make germ cells.
No protein condensates, no offspring. While beneficial for reproduction, other types of condensates can be very detrimental. They can harm cells and cause diseases like Alzheimer's or amyotrophic lateral sclerosis, ALS.
In a healthy cell, condensates form from condensation of individual proteins to form liquid-like structures. But in many diseases, such as ALS or Alzheimer's, you find aggregates of proteins. Aggregates are collections of proteins that are not dynamic. They just stay in one place, like a solid.
This is how such an aggregate forms. A specific protein named FUS turns from its liquid phase into a solid form. Tony Hyman discovered that this protein transformation may be a decisive factor for the onset of ALS. That these FUS proteins solidify may be the very cause why ALS patients lose the ability to move their muscles. The team can emulate protein hardening, normally caused by disease, artificially in the lab. Another candidate is the protein TAU, which plays a role in Alzheimer's disease. By adding chemical solutions or changing the temperature regime, the researchers simulate various conditions inside a cell to find out which variables may be responsible for creating unwanted protein lumps.
How's it going, Hero? All good? Yeah. You got some results then?
But they can do it the other way round as well, reliquefying solid proteins through chemical agents. A first step on the long path towards developing medication to treat ALS. On the left, FUS condensates with solid deposits, and on the right, the same proteins after treatment.
In the long term, I'm extremely optimistic because it's clear that you cannot think of a cell as a dilute solution of proteins that don't work together. That would be like thinking of a village as a set of individual people without working on the psychology of how groups form. So I'm absolutely convinced that by studying the cell, using these condensate ideas, in the long term, will revolutionize drug discovery.
Tony Hyman has changed how we look at the cells that make up our bodies, and his work promises even more important information on the various proteins that float in the intracellular fluid, where they can potentially form condensates. The functions these proteins have for our lives and in causing disease are not yet completely understood. But how condensates form and what brings proteins to change from a liquid to a solid state, understanding these mechanisms lays the foundation for future medical treatments.
My biggest wish is to understand how cells control the behavior of condensates, and that allows us to understand why they go wrong in disease.
So, you've seen the video. It's now time to meet the man himself. Please welcome to the stage Dr. Anthony Hyman. Well, we've just heard all about you, but I'd like to start with, just to set the scene perhaps, is that for the person walking around out there on the streets in Hamburg, why should they care about this discovery?
Well, if we think about the process of disease, you know, a doctor or a scientist might want to try to cure disease, but to do that, they have to understand how a cell works. It'd be like taking your car to the garage and the mechanic doesn't actually know how an engine works. How could they possibly repair it? And similarly, if we're going to cure disease, we have to understand how the cell works. And these discoveries were a basic way, one of the basic ways cells go about organizing themselves, and we can't understand how things go wrong unless we understand how they work correctly.
Well, I'd like to dig a little bit into cells, because we hear about them in society, we talk about them, but we don't often talk about the concept of a cell, you know, these little things that make up our bodies, what they are and what they're doing. So just to set the context here, just tell us, what is a cell? What does it do?
Well, in the end, we're a collection of cells, with trillions of cells in our body that forms a collective that, like any collective, obey the rules that are set. You know, the liver cells, and they should be liver, and the arm cells, and they should be arms. But they are their own living entity. They themselves have to make sure they take in enough stuff from the outside, make the right materials inside, divide when they should divide, die when they should die, and obey the rules. So that's what a cell does. Now, sometimes cells decide they don't want to obey the rules. We don't want to be part of this collective. And then that's when you get things like cancer. We're going to make our own little organism, and then you build some sort of tumor inside the body.
So, I mean, they sound, I think the concept of the inside of a cell, where it's a little molecular factory almost, you compared it to a village where there's all these, even inside the cell, there's lots of different things going on. They've got to coordinate. How, you know, what sort of tasks are going on? What's going on inside a cell?
Well, like a village, you know, for instance, you need energy. You have power stations, the mitochondria, or you have other types of machines that take sugar and make it into the energy stuff that we need. Or when we build our cells, we get bigger, we need more raw materials, so they bring in sugar and make raw materials out of them.
And so so we're coming to the condensates and how they are where do they fit into the cell machinery? You've got this cell, it's busy, it's doing all these things. Where are the condensates in all of that? Where are they sitting and what are they doing?
Well, the way I like to describe it is that, in a society, you know, we don't work as individuals, we work as groups. And there are types of groups that are together all the time, but there are kinds of dynamic groups that form, say like flash mobs. And the condensate is a dynamic process that forms just when the cell needs something, and it can be rapidly dissolved when it's not needed. There are other types of compartments, such as ones in membranes, which are much more stable, as an example, which might, like mitochondria, provide long-term energy usage.
So perhaps, you know, an analogy in society is that, you know, when it's time for school, the children all come to school and then they go away again. And
that's a very good example. Yeah, you know, everyone, the children, the parents may be in the cafes, then the bell rings, all the children know it's time to run into the playground, and they run around. They're very dynamic. They know they can't leave the school ground, but they sort of form this liquid-like drop in a sense.
And so the discovery of these condensates, I mean, there's lots of popular, you know, the ideas in films about how discoveries happen. But tell us a little bit about how this discovery was made. What was the moment when you thought this is different?
Well, we were in Woods Hole, which is an oceanographic institute on the east coast of the United States. And there was a physiology course that goes back to 1880, I think. And every year you have to take 10 students for 2 weeks and teach them. And you're meant to do new discoveries, new experiments. And so one year we gave the students the task of filming these pea granules in high time and spatial resolution. And then the movies came up on the screen, and we stood in front of the screen, and someone said, I think it's my colleague Frank Uliker, it's a liquid. And suddenly we thought, wow, I mean, that changes the way we think about the cell. You know, just an immediate realization this was something we'd never seen before.
So what was the previous idea of what was in a cell? What was the idea changing from to understand it was a liquid?
It's like one of these things, I think it's more a question. Often discoveries are you find a question no one actually thought to ask before, which was you have this complex biochemistry in one place, millions of proteins somehow. Why do they stay in one place? So when we saw that, we understood a question that we never asked before that could be explained by this idea.
And one of the nice things about this a piece of research from the outside, I think, is that it's really important because it's physics as well as biology. So traditionally in school, you know, the biologists sit over there and they study plants and animals and cells, and the physicists are over there studying balls falling off slopes and things like that. I'm a physicist, I'm allowed to say that. You know, they're seen as very separate things, but this is down at the level of molecules then. These two things are coming together. How is that, I mean, how well are we making those connections?
You know, I think there's a real understanding that we have to bring these fields together to make progress. I mean, that's generally understood. The question is how you make it work. And I think that was my great bit of luck, you know, like as luck in all discoveries, that when I was in Heidelberg, there was a physicist on sabbatical, chap called Stan Leibler, and I suddenly understood, yeah, physics is an important way of thinking about how cells organize. And then I had a great bit of luck in Dresden, that the Max Planck, at the same time as building our institute, decided to build the physics of complex systems, and hired a colleague of ours, Frank Uliker, and then together we started to explore how can we use physics to understand how this little C. elegans embryo started. And from that, working together for over 10 years, you know, we built the structures and thought processes to bring the two together.
So fundamentally down there at the level of molecules, you know, they're interacting with each other and they need physics rules as well as chemistry rules as well as the principles of biology. So you have to look at it all together.
Well, I think, you know, as you know, physicists are kind of an arrogant bunch, and they would say that actually, you know, it's all physics anyway, so there was no ever, all other fields were just sort of temporary, you know.
Well, let's not start the fight between the biologists and the physicists too soon. You can all do that in the drinks reception afterwards. So, and how easy is it to find out about what's happening inside a cell? You know, we hear about all these great discoveries, and sometimes on the television news, it's just as though somebody, you know, they just woke up one morning and happened to notice. How hard is it to get inside cells to watch the processes of life?
You know, it's an immensely complex process, and you can certainly say that it's advances in microscopy that have driven cell biology. Every time we make an advance, you know, there was original phase contrast microscopy going back a long time again, fluorescence, you know, all these different types of microscopy, one after another, many of which, you know, have led to Nobel Prizes. And all of those allow us to look deeper and better into the cell. So that's the basis of it all, and they take decades to, you know, to discover. So, and each time a new microscope comes in, what a cell biologist does, they look at their specimens again and say, could that help us? Right. You know, and then this case, it did, because it's a new type of microscope where we looked at it, and that gave us the resolution to look at the liquid-like state.
So you have a new pair of eyes.
Yeah, exactly, a new pair of eyes.
Things.
Yeah, it's true. It's like putting on glasses. Right. That's, yeah.
I think you're selling biology very well here. And how, you know, sometimes this is something scientists don't think about very much, that maybe you have, that how does it change the way you think about being human? Because, you know, we can all look in the mirror and we can see the view we're used to, or you can see, you can imagine all the little cells and organs doing things. Does this change sometimes do you ever pick something up and wonder what's happening inside those cells? Do you ever think about that?
Not every day, but every so often you do step back when you think about something. You think, how can this possibly work? It's so awesomely complex. So the one I always like to use is that if every cell has 5 billion proteins in it, roughly.
Can we just pause on that statement and say that again very slowly, because it's an incredible statement. Go on.
Yeah, every cell in our body has about 5 billion proteins, the population of the world.
That's in one cell?
One cell, and we have trillions of cells.
Okay, everyone just take a deep breath. Okay, so sorry, carry on. So, yeah.
Yes, so let's say you have 5 billion people in the world, and let's say a condensate has 1 million people, like the population of Hamburg. So you could say, oh, well, it's okay, I can imagine 1 million people coming together, they form a city, they do something, and they go away again. It'd be complex. But a cell is very different than that, because if you scale up proteins to be people, right? So you just say, let's take all the proteins and make them the size of people. And you ask, how dense would that be? We would all fit in Lake Como.
So this is a lot of people in a small
We'd
space.
be about this distance apart, swimming past each other about 3 square kilometers a second. And I remember the first time I did that calculation with some people in the lab thinking, that's just absolutely unbelievable. And looking at my cells suddenly differently and think, in every one of those cells, that process is happening all the time. So there are those moments where you think, it's just such an amazing process. It's a miracle, as I often like to describe, that could ever work. Yeah.
It is. I think whenever we see, athletes going off the blocks in a race and we think they've got quick reactions, it's humbling to slow down and think about how much is going on. Well, so we're discussing here cells when they're working well. And of course, there are lots of reasons for doing basic research for curiosity and for our perspective. But really, the immediate applications of this are disease. And so in the years, the first paper on this was published several years ago now. What doors have opened since then? Where does it look like this discovery might take us in terms of understanding disease?
I think we didn't think about disease very much at all at the beginning. But then in 2015, you made this discovery that these liquids, when you made them in a test tube, we were looking at them, and they suddenly became these solids. And then we began, and we knew about solids from disease, because every neurodegenerative disease, brain disease that goes wrong, or even the terrible disease when people hit the football too much, they have these protein aggregates. And so we thought, maybe that is the link for these diseases. And that was another extremely exciting moment. And then since then, we and others have begun to look for examples of where in disease the condensates are in the wrong place. Just to give you an example, a cell has a nucleus, if we think back about in our biology, and a membrane. I think most of us remember that part. And if a protein gets stuck out in the cytoplasm and it's needed in the nucleus, the cell can't work properly. And we've begun to discover more and more examples where the condensate is in the wrong place. And then the protein's in the wrong place, and then they can't work, right? So let's say, you go to visit another town next door, and they build a wall around it, you can't get out. Well, then you can't go back to your own town and bake some bread.
Right. So you're limited then, that all these very intricate processes are interdependent, and this one working depends on that one working, which depends on that one working.
Yes, in ways that are so complex we just don't understand most of them.
And how do you use, obviously these things are still being discovered, but might it be possible to have a medicine which alters the condensate? So how could we affect, it's one thing to watch it happening, but what could we do about it if it goes wrong?
Well, let's take the example of these liquid becoming more like solids. So in other words, a little bit like, you have a liquid maybe like honey, and then it becomes more and more so like a gel, like the jelly we have in England. I think luckily Germans don't know about it, but this disgusting jellies we had to eat as children. And then you could look for a medical...
It's great. We've got horrible jelly and we've got Brexit. It's wonderful in England. Carry on.
And so you could imagine the liquid-like drops turning into this more solid-like state, you could prevent that by adding a chemical. Right. And if you could slow that down, that might be a way to stop them becoming aberrant, as we call them, you know, wrong condensates.
So it's very, I mean, there's all of this intricacy, and it's an amazing thing to think about going in and tweaking it.
Yes.
But this is what modern science allows.
Exactly.
If we understand it well enough, tweaking is a possibility.
Tweaking is the crucial thing, exactly, yes.
And what sort of things have to happen? Obviously, there's lots more research to come, but what sort of thing, what do we need to do next in order to realize that potential?
You know, I think the thing about biology is just the unbelievable complexity. That's what puts so many people off. You know, because you make a discovery like liquid-like states, but then this incredible detail work has to begin, which you have to love. And the reason is that, you know, 3 billion years ago, when the first primitive soup, from which life came, had some probably reasonably primitive physics, you know, the type of physics that we learn about. But over 3 billion years, what has biology done to make that stable, work all the time? We live to 60, before most of us get diabetes. That means we've been eating sugar all the time, stressing our system, but the system's coping with that. And those are the rules, and that's incredibly complex. It's going to take decades to go through each one of these and really work out exactly, precisely how it works.
But if you don't start, you'll never get
exactly,
there.
You have to, yeah, exactly.
You have to get started.
Yeah.
And so is this, I mean, just in terms of, I know it's impossible to predict when things will happen, but how long do you think it will be before this might make a difference to therapies that people actually get?
Well, it's already made a difference in the following senses. If you take a drug and add it to a cell, you know, I think before these discoveries, people didn't really pay attention to the fact, where will that drug go in the cell? Will it go to a condensate or not? If your protein has gone wrong is in a condensate and your drug doesn't get there, what's the point? So just taking known drugs and looking at that, that's already people are thinking about that right away. So that's the first thing. And then I think, you know, the drug programs and cells that start from the beginning, they take a decade or something to get to work. But there are many biotech companies around the world, but also pharma companies beginning to use these ideas to think about how to make their drugs better.
And what does it, I mean, when you first published the paper, was the reaction positive immediately, or did it take a little while for everyone to realize how important it was?
You know, it was a sideshow. You go to the fair and you've got the main Ferris wheel and then it's some little stand on the outside. I mean, I think people, including us, understood it was a cool discovery, but we didn't understand in any way how broad the implications would be. So I think people thought, oh, it's a cool discovery. And then with time, as we spent more and more time on it, more and more demonstration in other systems, people began to understand that it might have, you know, more general application.
And what does it feel like to have this idea that you see something in a microscope with your team, and then you watch this idea roll out into the world, and there are other people writing papers based on this idea, and you've never met them, you've never seen their labs, you've no idea who they are, and how does that you know, you're just this idea, this baby just rolls off into the world, how does that feel?
Wonderful. You know, that is the hope of every scientist, I think, you know, that you develop some idea that changes the way people look at what they're doing in the cells. They have to take it and take it further, you know, because all we are as scientists in the end is we make discoveries and we hold the scientific method in trust for the next generation. We train our students, we train our postdocs. You know, I've had 50 scientists go through my lab, probably, and I sort of train them, and then, and that's, you know, so that's the wonderful feeling, because you know that your ideas have been carried forward into this community.
Passed on. Well, let's talk about your team and your lab, because, and actually back to the beginning, because I think for anyone, you know, I know you were talking to news reporters this morning, for anyone who sees that scientist on the news, and you're wearing a suit and you're in a posh hall and you're getting an award, and it feels a long way from everyday life in that context. When you were a kid, did you want to be a footballer, or did you want to be a fireman, or did you always want to be a scientist? How did you get started on all of this?
No, actually, I want to be a bicycle mechanic.
Right.
So I was never very good at school. You know, I did try hard because I knew it's important for my parents, but I just didn't do well in exams. You know, wasn't lazy. And it didn't even occur to me to go to university at the beginning because I didn't do well enough in my A-levels, so I became a lab technician because my friend Raf and I wanted to build a bike shop.
Right.
He was a jazz bass guitarist, and I went to work in the lab. And he's still playing jazz bass, and I'm still in the lab. Because once I got there, I understood there was an aspect of what I was really good at, which was very good with my hands, you know, and so I could make experiments work well. And then I got more and more into it, and then I went to university, and then all these courses on these incredible molecular machines inside cells, and I was thinking, oh, I want to work on these machines. And then I got started, and then the rest is history, really. Just stuck with it, and then ended up where I am here.
So not a bicycle mechanic, but a cell mechanic.
Cell mechanic, exactly. Exactly.
And what drives, you know, so I think a lot of scientists, it's easy, you get up in the morning, a lot of people, you know, you just sort of do your job because that's what's in front of you. What drives you in how you choose the scientific questions you choose to work on, or you know, those directions? Is it just curiosity? Is it because it could help people? Is it because science is fun? What gets you out of bed in the mornings?
You know, I mean, the basis of being a good scientist is curiosity, and I always say that to people. You know, you've got to get up every morning and want to understand how it works. I mean, without that, you can't be a scientist. But there's another thing, I think, which is important in driving discovery, is discontent, right? You have to have this constant discontent with what you've done to make you do the next thing. My father used to call it divine discontent, you know, is that, you know, it's, and I think that's a crucial thing. You do something, instead of sitting on your laurels thinking, oh, that was great, then you think, that was okay, but so-and-so, I've got to do more. And those two things, I think, are what keep you going as a scientist. You know.
I think you probably have to come, I mean, it sounds not unhealthy, but something you have to keep an eye on.
Yeah.
Are you a perfectionist, or are you just...
No, I'm not really a perfectionist. I just, I get bored quickly. So therefore, if I'm doing something for a while, and then nothing new's happening, I get bored and I want to move to the next thing, you know, sort of, and so that's been a crucial part of, you know, keeping me going through all the long period of being a scientist, because it is a long-term process, making discoveries.
Are you a patient man?
I am patient, yes. Relatively patient, yeah. You have to ask my children. Ask Luke what he thinks.
And so let's come to teamwork then, because, I mean, it is true, you are being honoured for this award, but of course there was a team around you, there's a team in the past. Tell us a little bit about the teamwork you do and who's on that team.
Yeah, I mean, I think science is a curious business, because if you make a discovery like we did in 2009, you have the time leading up to it, which later, and you've got the time afterwards where you actually show that it was important. And you can't be a scientist without the teamwork that goes behind it. If you think in my case, of course, there's the group, right, the scientists, the students and postdocs, over 30 years, 50 of them have gone through my lab. I mean, without them, they did all the work. It's impossible. But then, being a scientist, this discovery, you could say, took 30 years to where we are today, and that requires long-term support. And so, for instance, in my case, a crucial part of the teamwork was the founding directors. You know, it was Ivan Baines, Joe Howard, Wieland Huttner, Kai Stevens, Marina Zerial, all of us who in 1996 thought, let's go east. You know, let's go to Dresden, start a new Max Planck Institute. So that teamwork of over so long provides a stability that allows you to do these discoveries, you know, every day. And then you have your collaborators, you know, people you've worked with over the years. Stefan Grill, who's in the audience, a crucial part of developing the physics, Simon Alberti, others. And so I like to describe it a little bit like a universe. You know, you've got the sun, which is your stable core, but there's a whole set of planets have to revolve around it, your collaborators, your groups, other people, to make that system. You have to be stable. And then, of course, the family structure, right? Without a family structure over the time, you can't be stable. In my case, you know, my wife, you know, Suzanne Eaton, I'd like to, you know, dedicate this to her. You know, we lost her in a appalling tragedy in 2009, and, you know, without her love, affection, and intelligence, you know, none of this would have been possible. And, you know, these are the things that all have to fit together over a long period to be a scientist. It was like Peter Medawar said in one of his books, you know, an artist like Van Gogh can cut off his ear, and everyone goes, wow, cut off his ear, that's a great thing. But a scientist cut off their ear, they would lose their job the next day. So, you know, so for us it's stability, quiet, just, you know. So.
But it's important, isn't it, to recognise that science is a human endeavour, and for all we hold up the ideals of science as being objective and not influenced by, you know, our personal preferences, the best thing about it is that it's human, that we are humans working on teams with other humans, and we are enjoying the best, you know, the curiosity. These are very human things, aren't they?
It's the most human of all occupations, being a scientist, because there's no obvious, you know, like you don't make money like in a company. There's no, what is the actual output? And so in the end, what the output is, the way people work together in these teams and enjoy the teamwork, I would say. That's what people love about working in a lab often, is the constant teamwork you do over long periods. And that, the way that team works is fundamental for discovery. If it doesn't work, you don't make discoveries. And so a huge amount of the work as an institute director group is about making people work well together and giving them conditions to feel happy. And because science takes such a long time, you know, discoveries, 30 years, the long-term trust. You know, if I work, I will be supported over a long period of time. You know, and that, of course, is a great thing about the Max Planck Society, for which, you know, these discoveries wouldn't have happened, because it's the last organization left, I know, in the world that says, 36, Tony, here's money to retire, make some discoveries. And those...
So you were 36 years old when they put that trust in you.
Yeah, they did, exactly. You know, and those are probably special times after the wall came down. You know, who were the crazy people who would go east at the time? And you know, that allows you then to do long-term discoveries. You have the trust. If it doesn't work, the money's still there.
To have faith in the science. Yeah. Well, you have some quite perhaps unorthodox members of your team, your dogs,
yes.
who come with you quite a lot. So tell us a little bit about your dogs.
Well, they're two whippets, racing dogs, rabbit hunters, in theory, although we never let them hunt a rabbit. But there was an outbreak of rabbits recently in Dresden that made life extremely complicated. Because, and yeah, that's, so they go with me everywhere. You know, the whippets, as my father used to say, they're lovely animals, but not dogs. You know, if you have a Labrador and you get home, it's always happy. But these dogs, they mirror your emotions, so it's even worse. You get home, you've had a bad day, they're suddenly unhappy, so then you have to make them happy. But it's, yeah.
So you have to face up to yourself that day.
Yeah, they make you face up to yourself every day, exactly. Yeah.
And do they stop you working all the time, or you know, do you sort of find time away from the lab? What do you do? Do you relax? It's always a difficult question to ask a very accomplished scientist, because many of them don't admit to relaxation. Do you relax?
Actually, I mean, I do. In fact, I'm known for relaxing. My nickname in the cycling club in Dresden is Kaffee Pause Hyman, because because every time we go somewhere, I want to stop for a coffee. So I do a lot of cycling. That's how I relax my. And I also play the flute, and so that was wonderful to listen to such a young, accomplished flautist. I'll never be as good as him, but it's still something which relaxes me and switches your mind off. You know, so music and exercise provide these two sort of alternative ways for your brain to work.
I often wish, so my students at University College London, they sometimes say, oh, I'm too busy doing science and engineering to do sport and music. And I want to say to them exactly that no, you need to be a good scientist, you need to allow your mind space. It's like having space, isn't it, to let your mind do something else.
I think that's a good way to say it. I mean, I often say also to my students is that, you know, the discoveries don't come from your thinking process, they come from the subconscious. The brain puts it all together, but how can the brain put it together unless it has the facts? That's the fuel of the brain. You have to fill it with facts and then stop. Like sleep over it, the classic thing we know, you know, or the phrase, the morning is clever than the evening, that's a German phrase also. And, you know, and that's why I stop.
So some condensates have to have some work to do.
Exactly, they can go in, exactly.
And so then, you know, looking to the future, what are you most excited about, either professionally or personally? What are the big things that you're excited about coming down the line?
You know, at a sort of professional level, I'm, you know, still super excited about finding out how condensates are controlled. You know, that is wonderful, new people coming in every day. You know, I'm excited. I think the older one gets, the more excited one becomes about drug discovery and making sure that the discoveries we made have some application in medicine. And then otherwise, you know, it's the great thing about a scientist, because you never know. You come in every day, and a student or a postdoc comes to you and says, look at this, and you go, oh, wow, maybe I need to work on that, just like we did in 2009. So.
Well, that is a beautiful way to finish.
Yeah, yeah.
Please, everyone, join me in congratulating Dr. Anthony Hyman. So to follow on from that, I would like to invite Tatjana Koenig, who is a member of the executive board of the Körber-Stiftung, and also Martin Strachman, the president of the Max Planck Society and chairman of the trustee commission for the Körber Prize, to come to the stage. So we've heard about the nitty-gritty of the science, and we're going to deal here with some of the bigger picture stuff to take a step back. So Tatjana, first of all, could you just set out, we heard a little bit about Kurt Körber before, but could you set out why, the background for the Körber Prize, and why this focus on European science was so important to Körber?
I think what we need to know, beside the fact that Körber was a very innovative, entrepreneurial type, he was very much influenced by the fact that he lived through, in his early stage careers, through the Third Reich. He survived literally by chance the bomb raid of the British in February 1945, and he then left the GDR in order to start his new company in Hamburg. So, having been born in Berlin and having lived through all these times with the Iron Curtain, the Pershing missiles, you know, being stationed in the West, and with this very tense political setup the Cold War was, he believed very much in people, and that people should come together, and that they should know each other. He didn't only believe in that in the scientific context, but he wanted to award a prize to those who, despite the fact that they're divided in political blocs, work together on a research mission. And that's how, and Peter Center already described it, the first years the prize was given to teams from the East and the West. And I think it's so beautiful to think, you know, that despite the fact that Germany attacked all of Europe, and then as a consequence the British bombed Dresden, today this award goes to a British biologist who actually works in Dresden. I'm sure that Kurt Körber would have absolutely loved that.
Thank you, yes. So, Martin, why is Tony Hyman such a good example of the sort of thing that the Körber Prize would like to reward?
Well, I could mention two reasons. First and foremost, he's an outstanding scientist. I have to say he's a real star of our society. That's, of course, the most important fact, I have to say. Second, I think you heard the history of Körber. You heard the history that Körber started in Dresden. He moved on later to Hamburg. And Tony was one of the first scientists who went to the eastern part of Germany after unification. He built up an institute there. He was formerly employed by the European Laboratory for Microbiology, which is a famous institution in Europe. And what is, I think, most important, he just did not copy what we have done in the West. This institute he's responsible for is unique. This institute has a special structure. If you look at that institute, if you go in there, you don't see this columnar Max Planck Institute, you sometimes see with the directors on top. You see many young people, very many young people. They have given up, I have to say this here, their own budgets, the real budgets they got as directors in order to promote young scientists, which is, I would say, very specific, very special. So if you go to Dresden today and you will see how important Dresden is as a science city, then it's to a large extent also due to Tony Hyman and his colleagues.
And what's the, stepping back a little bit further, you know, we, as scientists, we can sit in our labs and we can do our science, but also it feels like science has a bigger role. You know, there's a global role. There's some things that science can perhaps set an example for. So what's the global role, perhaps, Martin, the global role for science in society? How should we connect to the rest of society?
Well, I could give many examples, and I wouldn't have the time to do this here, to show many examples how important science is. So let me step back a bit and look at this from a more bird's perspective of view. And then I have to say, science, it's part of us. Science is part of humans. We have the brain to do science. We are the only species in this globe who can understand our environment, who can shape the environment, who can live under very nasty conditions and survive. For example, we don't want to be eaten up by a virus. We fight for that virus. So if you look back in what we are as humans, I would say humans are as successful as they are because they do science. So for the whole history of human mankind, we have tried to understand the world we live in, and we have a second ability which is unique. We have language. So we can transport the knowledge, we can hand over this knowledge to the next generation. So we accumulate knowledge year by year, decade by decade, century by century. And for that reason, I would say science is a human heritage. Science does not belong to Tony. It doesn't belong to the Max Planck Society. It doesn't belong to Germany. Why do we publish scientific results? Why do we lay it open in China, in Russia, in the US, in Germany? We lay it open because we want to build a whole block, a whole building of understanding. And for that reason, I think science should not be misused as part of, let me say, the competition between states, between regions, between continents. Science belongs to all of us, and I think we all, if we wouldn't have science, honestly, we would have a very nasty life, a very primitive life, a life as all the other animals we see around. In fact, we are different from all of them, and the only reason we are different is honestly science. So if you ask me how important is science, I think it's as important as having our daily food.
And Tatiana, how does the Körber Foundation see its role in, you know, we've got these ideals of science. What does the foundation see that it wants to do in this space?
Well, we are so incredibly lucky that Kurt Körber left us his wealth so that we could, you know, put into practice what he already created or thought of. And when we want to promote science and education, actually, because Kurt Körber was convinced that you need education, you need science in order to have a prosperity in society, and that prosperity and democracy are very closely linked together. So if we want to have, you know, stable conditions in order to thrive and do more science, we have to support those who do research. And he very much believed, when awarding the prize, that it could be you know, an assistance in rediscovering a common European scientific community, and to you know, bridge differences there might be through politics, and to really underline how important it is that we get together, that it's a joint effort. You know, being successful, Tony said it, it's a team effort, and it's something we really deeply want to support.
And Martin, I just want to pick up on the definition of European, because that itself is a political thing. So how should we think about being European in this context?
Well, first of all, Europe is highly successful in science. We should see Europe as a whole entity. We should not see Europe only as a European community, that I have to say. Science goes beyond. And I'm looking at the EMBL, the European Laboratory for Microbiology. This is an enterprise which is carried upon by many states in Europe, but it goes beyond the European community. So I think these days where we have the split we have experienced the split of Britain, we have seen the split of Switzerland, I think that is a very dangerous development, and we should really see that Europe as a whole continent can do great science, but it should not limit its science to the European community only. And second, I have to say, Europe is made up of very small countries in general. So we have to team up, and we have the ability to team up. We have seen this. EMBL is one example. The Southern Observatory, the ESO, is another example. The ESA, the European Space Agency, CERN, I could give many examples. So we have come up with structures in Europe which allow us to team up. And honestly, this is a specificity of European science. You won't find this in the US, which is a much larger state. You won't find this in China. So I think Europe has shown that beyond the interest of individual states, we can team up to solve larger problems. And I think that's a richness, I have to say, of European science.
Well, that is a great point to move on, because we are here for an award. This is a ceremony, and therefore there has to be the presentation of the award, and that is what we're going to move on to now. And I would like to invite Lothar Dittmar and Anthony Hyman to come, and Martin Strachman will carry out the presentation. Please give our two speakers a round of applause while that happens.
Yeah, I may now read at first the laudatio. Anthony Hyman is awarded for the discovery of a completely new state of biological matter. Together with his team, Hyman discovered that proteins can accumulate locally in high concentrations in the cell fluid. He developed a whole arsenal of methods to observe condensates and better understand their function. Condensates hold the key to some of the cell biology's biggest unanswered questions. This new cell biological understanding of condensate formation will have an important impact on the prevention of diseases and future drug development.
So we are now very near to the last step of the prize ceremony. In accordance with the proposal of the appointed Board of Trustees, the Körber-Stiftung awards the Körber European Science Prize 2022 for groundbreaking discoveries in cell biology to Professor Dr. Anthony Hyman, Max Planck Institute of Molecular Cell Biology and Genetics, Dresden. Congratulations, herzlichen Glückwunsch.
So, to conclude our ceremony today, I would like to invite our musicians back, and they will play this time the Sonatina for flute and piano by James Ray, Aquarelle, and Fire Dance. So please welcome our musicians. Thank you very much to our musicians. Ladies and gentlemen, we've reached the end of the ceremony. I hope that your heads are full of ideas and science and optimism about the future. And to thank you all for coming, and also to thank everyone watching the live stream for joining in with this. Now, to discuss all those things in your heads, all those science and ideas and optimism, you're all invited to a champagne reception. So the doors on this side will open. All of you are welcome to walk into the room next door to take your champagne and continue the celebrations. But thank you once again for joining us, and please, one final round of applause for Dr. Anthony Hyman.